Hello everyone, welcome to EduHub Vidyarthi. Today we are going to do chapter solutions, which is the first chapter for chemistry class 12. Starting with unit 2, solutions. Almost all processes in body occur in some kind of liquid solutions. In normal life, we rarely come across pure substances. Most of these are mixtures containing two or more pure substances. Their utility or importance in life depends on their composition. For example, the properties of brass, which is the mixture of copper and zinc, are quite different from those of German silver, which is a mixture of copper, zinc, and nickel, or bronze, which is the mixture of copper and tin. 1 part per million of fluoride ions in water prevents tooth decay, while 1.5 parts per million causes the tooth to become mottled, and highly concentration of fluoride ions can be poisonous. For example, sodium fluoride is used in rat poison. Intravenous injections are always dissolved in water containing salts at a particular ionic concentrations that match with the blood plasma concentrations, and so on. In this unit, we will consider mostly liquid solutions and their formation. This will be followed by studying the properties of the solutions like vapor pressure and colligative properties. We will begin with the types of solutions and then various alternatives in which concentrations of solute can be expressed in a liquid solution. Types of solutions. Solutions are homogeneous mixtures of two or more than two components. By homogeneous mixture, we mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in the largest quantity is known as solvent. The solvent determines the physical state in which solution exists. One or more components present in a solution other than solvent are called solutes. In this unit, we shall consider only binary solutions, that is, consisting of two components. Here, each component may be solid or liquid or in gaseous state and are summarized in table 2.1. You can have a look at table 2.1. 2.2. Expressing concentrations of solutions. Composition of a solution can be described by expressing in concentration. The latter can be expressed either qualitatively or quantitatively. For example, qualitatively, we can say that solution is dilute, that is relatively very small quantity of solute, or it is concentrated, that is relatively very large quantity of solute. But in real life, these kind of description can add a lot of confusion, and thus the need for quantitative description of the solution. There are several ways by which we can describe the concentration of solution quantitatively. 1. Mass percent. Weight by weight. The mass percentage of a component of a solution is defined as mass of the component in solution upon total mass of the solution into 100. For example, if a solution is described by 10% glucose in water by mass, it means that 10 gram of glucose is dissolved in 90 gram of water, resulting in a 100 gram solution. Concentration described by mass percentage is commonly used in industrial chemical applications. For example, commercial bleaching solutions contain 3.62 mass percentage of sodium hypochlorite in water. 2. Volume percentage, V by V. The volume percentage is defined as volume of the component upon the total volume of solution into 100. For example, 10% ethanol solution in water means 10 ml of ethanol dissolved in water such that the total volume of the solution is 100 ml. Solutions containing liquids are commonly expressed in this unit. For example, 35% V by V solution of ethylene glycol and antifreeze is used in cars for cooling the engine. At this concentration, the antifreeze lowers the freezing point of water to 255.4 Kelvin or minus 17.6 degrees Celsius. Third, mass by volume percentage, weight by volume. Another unit which is commonly used in medicine and pharmacy is mass by volume percentage. It is the mass of solute dissolved in 100 ml of the solution. 4. ppm, parts per million. When a solute is present in trace amount, it is convenient to express concentration in parts per million and is defined as number of parts of component upon total number of parts of all the components into 10 to the power 6. As in the case of percentage, concentration in parts per million can also be expressed as mass to mass, volume to volume, and mass to volume. A liter of seawater, which weighs 1030 gram, contains about 6 into 10 to the power minus 3 gram of dissolved oxygen. Such a small concentration is also expressed as 5.8 gram per 10 to the power 6 gram, which is 5.8 parts per million of sea water. The concentration of pollutants in water or atmosphere is often expressed in the terms of microgram per milliliter or ppm. Fifth, mole fraction. Commonly used symbol for mole fraction is X, and subscript used on the right hand side of X denotes the component. It is defined as mole fraction of component equals number of moles of component upon total number of moles of all the components. For example, in a binary mixture, if number of moles of A and B are Na and Nb respectively, the mole fraction of A will be chi A equals Na upon Na plus Nb. For a solution containing I number of components, we have chi I equal Ni upon N1 plus N2 till Ni. It can be shown that in a given solution, sum of all the mole fractions is in unity, which is equal to 1. Mole fraction unit is very useful in relating some physical properties of solutions, say vapor pressure, and the concentration of solution, and quite useful in describing the calculations involving gas mixtures. 6. Molarity. Molarity M is defined as number of moles of solute dissolved in 1 liter or 1 cubic decimeter of solution. Molarity equals moles of solute upon volume of solution in liter. For example, 0.25 mole per liter or 0.25 m, which is molarity, solution of NaOH means 0.25 mole of NaOH has been dissolved in 1 liter or 1 cubic decimeter. 7. Molality, small m, is defined as the number of moles of solute per kilogram of solvent and is expressed as m equals moles of solute upon mass of solvent in kg. For example, 1 mole per kg solution of KCl means that 1 mole of KCl is dissolved in 1 kilogram of water. Each method of expressing concentration of solution has its own merits and demerits. Mass percent, ppm, mole fraction, molality are independent of temperature, whereas molarity is a function of temperature. This is because volume depends on temperature and mass does not. 2.3 Solubility. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent or at a specified temperature. It depends upon the nature of solute and solvent as well as the temperature and pressure. Let us consider the effect of these factors in a solution of solid or a gas in a liquid. 2.3.1 Solubility of a solid in a liquid. Every solid does not dissolve in given liquid, while sodium chloride and sugar dissolve readily in water. Naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. It is observed that polar solutes dissolve in polar solvents and non-polar solutes in non-polar solvents. In general, a solute dissolves in solvent if the intermolecular interactions are similar in the two, or we may say like dissolves like. When a solid solute is added to the solvent, some solute dissolves and its concentration increases in the solution. This process is known as dissolution. Some solute particles in solution collide with the solid solution particles and get separated out of the solution. This process is known as crystallization. A stage is reached when two processes occur at the same rate. Under such condition, the number of solute particles going into the solution will be equal to the solute particles separating out, and a state of dynamic equilibrium is reached. At this stage, the concentration of solute in solution will remain constant under the given conditions, that is temperature and pressure. Similar process is followed when gases are dissolved in liquid solvents. Such a solution which is no more solute can dissolve at the same temperature and pressure is called a saturated solution. An unsaturated solution is one in which more solute can be dissolved at the same temperature. The solution which is in dynamic equilibrium with undissolved solute is a saturated solution and contains the maximum amount of solute dissolved in given amount of solvent. Thus, the concentration of solute in such a solution is its solubility. Earlier, we have observed that solubility of one substance into another depends on the nature of the substances. In addition to these variables, two other parameters, that is temperature and pressure, also control the phenomenon. Effect of temperature. The solubility of a solid in a liquid significantly affected by temperature changes. Consider the equilibrium represented by equation 2.10. This, being dynamic equilibrium, must follow Le Chatelier's principle. In general, if in a nearly saturated solution the dissolution process is endothermic, delta H is greater than 0, then the solubility should increase with the rise in temperature, and if it is exothermic, the solubility should decrease. These trends are also observed experimentally. Effect of pressure. Pressure does not have any significant effect on solubility of solids in liquid. It is so because solids and liquids are highly incompressible and practically remain unaffected by changes in pressure. Solubility of gas in a liquid. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. It is this dissolved oxygen which sustains all aquatic life. On the other hand, hydrogen chloride gas is highly soluble in water. Solution of gas in liquids is greatly affected by pressure and temperature. The solubility of gases increase with increase of pressure. For solution of gases in a solvent, consider a system as shown in figure 2.18. The lower part is the solution and the upper part is the gaseous system at pressure P and temperature T. Assume that this system to be in a state of dynamic equilibrium. That is, under these conditions, rate of gaseous particles entering and leaving the solution phase is the same. Now, increase the pressure over the solution phase by compressing the gas to a smaller volume, that is figure 2.1b. This will increase the number of gaseous particles per unit volume over the solution and also the rate at which these gaseous particles are striking the surface of solution to enter it. The solubility of gas will increase until a new equilibrium is reached, resulting in an increase in the pressure of gas above the solution, and thus its solubility increases. Henry was the first to give a quantitative relation between pressure and solubility of a gas in a solvent, which is known as Henry's law. This law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of gas present above the surface of liquid or solution. Dalton, a contemporary of Henry, also concluded independently that the solubility of gas in liquid solution is a functional of partial pressure of gas. If we use the mole fraction of gas in the solution as a measure of its solubility, then it can be said that the mole fraction of gas in the solution is proportional to the partial pressure of the gas over the solution. The most commonly used form of Henry's law states that the partial pressure of the gas in vapor phase P is proportional to the mole fraction of the gas chi in the solution, and it is expressed as P equals Kh into X. Here Kh is the Henry's law constant If we draw a graph between partial pressure of the gas versus the mole fraction of the gas solution, then we should get a plot of the type as shown in figure 2.2. You can see the figure 2.2. Different gases have different KH values at the same temperature. This suggests that KH is a function of nature of gas. It is obvious from the equation 2.11 that higher the value of KH at a given pressure, lower is the solubility of gas in the liquid. It can be seen from table 2.2 that KH values for both N2 and O2 increase with increase of temperature, indicating that the solubility of gases increase with decrease of temperature. It is due to this reason that aquatic species are more comfortable in cold waters rather than warm waters. Henry's law finds several applications in industry and explains some biological phenomena. Notable among these are: 1. To increase the solubility of CO2 in soft drinks and soda water, the bottle is sealed under high pressure. 2. Scuba divers must cope with high concentration of dissolved gas while breathing air at high temperature underwater. Increased pressure increases the solubility of atmospheric gases in blood. When the divers come towards the surface, the pressure gradually decreases. This release of dissolved gases and leads to the formation of bubbles of nitrogen in the blood. This blocks the capillaries and creates a medical condition known as bends, which are painful and dangerous to life. To avoid bends, as well as the toxic effects of high concentration of nitrogen in the blood, the tanks used by scuba divers are filled with air diluted with helium, which is 11.7% helium, 56.2% nitrogen, and 32.1% oxygen. Third, at high altitude, the partial pressure of oxygen is less than that of the ground level. This leads to the low concentration of oxygen in the blood and tissues of the people living at high altitudes or climbers. Low blood oxygen causes climbers to become weak and unable to think clearly. Symptoms of this condition is known as anoxia. Effect of temperature. Solubility of gases and liquids decrease with rise in temperature. When dissolved, the gas molecules are present in liquid phase, and the process of dissolution can be considered similar to condensation, and heat is evolved in this process. We have learned in the last section that dissolution process involves dynamic equilibrium and thus must follow Le-Chatelier's principle. As dissolution is an exothermic process, the solubility should decrease with increase of temperature. 2.4 Vapor pressure of liquid solutions. Liquid solutions are formed when solvent is liquid. The solute can be of gas, a liquid, or a solid. The solutions of gases in liquids have already been discussed in section 2.32. In this section, we shall discuss the solutions of liquids and solids in a liquid. Such solutions may contain one or more volatile components. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the properties of one of only binary solutions, that is, the solutions containing two components, namely the solutions of liquid in liquid and solid in liquid. Let us consider a binary solution of two volatile liquids and denote the two components as 1 and 2. When taken in a closed vessel, both the components would evaporate and eventually an equilibrium would be established between the vapor phase and the liquid phase. Let the total vapor pressure at this stage be P total, and P1 and P2 be the partial vapor pressure of the two components 1 and 2. These partial pressures are related to the mole fractions chi1 and chi2 of the two components 1 and 2 respectively. The French chemist Francois Marthe-Rault gave the quantitative relationship between them. The relationship is known as the Raoult's law, which states that for a solution of volatile liquid, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. Thus, for component 1, P1 is directly proportional to chi1 and P1 equals P1 naught chi1, where P1 naught is the vapor pressure of pure component 1 at the same temperature. Similarly, for component 2, P2 equal to P2 naught chi2, where P2 naught represents the vapor pressure of the pure component 2 According to Dalton's law of partial pressure, the total pressure P total over the solution phase in the container will be the sum of partial pressures of the components of solution and is given as P total equals P1 plus P2. Substituting the values of P1 and P2, we get P total equals chi1 P1 naught plus chi2 P2 naught, which is further equal to P1 naught plus P2 naught minus P1 naught into chi2. The following conclusions can be drawn from equation 2.16. Total vapor pressure over the solution can be related to the mole fraction of any component. Total vapor pressure over the solution varies linearly with the mole fraction of the component 2. Third, depending on the vapor pressure of the pure component 1 and 2, the total vapor pressure over the solution decreases or increases with the increase of mole fraction of component 1. A plot of P1 and P2 versus the mole fraction chi1 and chi2 for a solution gives the linear plot as shown in figure 2.3. These lines 1 and 2 pass through the points for which chi1 and chi2 are equal to unity. Similarly, the plot of line 3 of P total versus chi2 is also linear. The minimum value of P total is P1 naught and the maximum value of P total is P2 naught, assuming the component 1 is less volatile than the component 2. The composition of vapor phase in the equilibrium with the solution is determined by the partial pressures of the components. If y1 and y2 are the mole fractions of the components 1 and 2, respectively in the vapor phase, then using Dalton's law of partial pressure, P1 naught is equal to y1 P total, P2 is equal to y2 P total. In general, P1 Pi equal to yi into P total. 2.4.2 Rolle's law as a special case of Henry's law. According to Rolle's law, the vapor pressure of volatile container component in a given solution is given by Pi equal to chi Pi naught. In the solution of a gas liquid, one of the component is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law, which states that P equals kHx, chi. If we compare the equations for Rolle's law and Henry's law, it can be seen that the partial pressure of volatile component or gas is directly proportional to its mole fraction of the solution. Only the proportionality constant Kh differs from P1 naught. Thus, Rolle's law becomes a special case of Henry's law in which Kh becomes equal to P1 naught. 2.4.3 Vapor pressure of a solution of solids in liquids. Another important class of solutions consists of solids dissolved in liquid. For example, sodium chloride, glucose, urea, and cane sugar in water, and iodine and sulfur dissolved in carbon disulfide. Some physical properties of these solutions are quite different from those of pure solvents. For example, vapor pressure. We have learnt in Unit 5, Class 11, that the liquids at a given temperature vaporize, and under equilibrium conditions, the pressure exerted by the vapors of the liquids over the liquid phase is called vapor pressure. In a pure liquid, the entire surface is occupied by the molecules of the liquid. If non-volatile solute is added to a solvent to give a solution, the vapor pressure of the solution is solely from the solvent alone. The vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. In the solution, the surface has both solute and solvent molecules. Thereby, the fraction of the surface covered by the solvent molecules gets reduced. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced. Thus, the vapor pressure is also reduced. The decrease in the vapor pressure of the solvent depends on the quantity of non-volatile solute present in the solution, irrespective of its nature. For example, decrease in the vapor pressure of water by adding 1 mole of sucrose to 1 kg of water is nearly similar to that produced by adding 1 mole of urea to the same quantity of water at the same temperature. Rolle's law, in its general form, can be stated as for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, only the solvent molecules are present in its vapor phase and contribute to vapor pressure. Let P1 be the vapor pressure of solvent Chi1, be the mole fraction, P1 naught be its vapor pressure in the pure state. Then, according to Raoult's law, P1 is directly proportional to Chi1 and P1 is equals to Chi1 P1 naught. The proportionality constant is equal to the vapor pressure of pure solvent P1 naught. A plot between vapor pressure and mole fraction of the solvent is linear. Ideal and non-ideal solutions. Liquid solutions can be classified into ideal and non-ideal solutions on the basis of Raoult's law. The solutions which obey Raoult's law over the entire range of concentration are known as ideal solutions. The ideal solutions have two other important properties. The enthalpy of mixing of the pure components to form the solution is 0 and the volume of mixing is also 0. That is, delta mixing H equals 0 and delta mixing V equals 0. It means that no heat is absorbed or evolved when the components are mixed. Also, the volume of solution would be equal to the sum of the volumes of the two components. At molecular level, ideal behavior of the solutions can be explained by considering the two components A and B. In pure components, the intermolecular attractive interactions will be of types AA and BB, whereas in the binary solution, in addition to these interactions, AB type of interaction will also be present. If the intermolecular attractive forces between AA and BB are nearly equal to those AB, this leads to the formation of ideal solution. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Solution of N-hexane and N-heptane, bromoethane and chloroethane, benzene and toluene, etc. fall into this category. When a solution does not obey Raoult's law over the entire range of concentration, then it is called a non-ideal solution. The vapor pressure of such a solution is either higher or lower than predicted by the Raoult's law. If it is higher, the solution exhibits positive deviation, and if it is lower, it exhibits negative deviation from Raoult's law. The plots of vapor pressure as the function of mole fraction for such solutions are shown in figure 2.6. The cause for these deviations lie in the nature of interactions at the molecular level. In case of positive deviation from Raoult's law, AB interactions are weaker than those of AA and or BB. That is, in this case, the intermolecular attractive forces between the solute-solvent molecules are weaker than those between the solute-solute and solvent-solvent molecules. This means that in such solutions, molecules of A or B will find it easier to escape than in pure state. This will increase the vapor pressure and result in positive deviation. Mixture of ethanol and acetone behave in this manner. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecule get in between, and the host molecules break some of the hydrogen bonds between them. Due to weakening of interactions, the solutions show positive deviation from Raoult's law. In a solution formed by adding carbon disulfide to acetone, the dipolar interactions between solute-solvent molecules are weaker than the respective interactions among the solute-solute and solvent-solvent molecules. The solution also shows positive deviation. In case of negative deviation from Raoult's law, the intermolecular attractive forces between AA and BB are weaker than those between AB and leads to decrease in vapor pressure, resulting in negative deviations. An example of this type of mixture is phenol and aniline. In this case, the intermolecular hydrogen bonding between phenolic proton and lone pair of nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between similar molecules. Similarly, a mixture of chloroform and acetone forms a solution with negative deviation from Raoult's law. This is because chloroform molecule is able to form hydrogen bond with acetone molecule as shown. This decreases the escaping tendency of molecules for each component and consequently the vapor pressure decreases, resulting in negative deviation from Raoult's law. Some liquids on mixing form azeotropes, which are binary mixtures having the same composition in liquid and vapor phase and boil at the constant temperature. In such cases, it is not possible to separate the components by fractional distillation. There are two types of azeotropes called minimum boiling azeotrope and maximum boiling azeotrope. The solutions which show a large positive deviation from Raoult's law form minimum boiling azeotrope at a specific composition. For example, ethanol water mixture obtained by fermentation of sugars on fractional distillation gives a solution containing approximately 95% by volume of ethanol. Once this composition, known as azeotrope composition, has been achieved, the liquid and vapor have the same composition and no further separation occurs. The solutions that show large negative deviation from Raoult's law form maximum boiling azeotrope at a specific composition. Nitric acid and water is an example of this class of azeotrope. This azeotrope has the approximate composition 68% nitric acid and 32% water by mass with a boiling point of 393.5 Kelvin. Colligative properties and determination of molar mass. We have learnt in section 2.4.3 that the vapor pressure of a solution decreases when a non-volatile solute is added to a volatile solvent. There are many properties of solutions which are connected with this decrease of vapor pressure. There are 1. Relative lowering of vapor pressure, 2. Depression of freezing point of the solvent, 3. Elevation of boiling point of the solvent, and 4. Osmotic pressure of the solution. All these properties depend on the number of solute particles irrespective of their nature relative to the total number of particles present in the solution. Such properties are called colligative properties. Colligative, from Latin co means together, ligare means to bind. In the following sections, we will discuss these properties one by one. Relative lowering of vapor pressure. We have learned in section 2.4.3 that the vapor pressure of a solvent in solution is less than that of the pure solvent. Raoult established that the lowering of vapor pressure depends only on the concentration of solute particles and it is independent of their identity. The equation 2.20 given in section 2.43 establishes a relation between the vapor pressure of the solution, mole fraction, and the vapor pressure of the solvent. That is, P1 is equals to x1 P1 naught. The reduction of vapor pressure of solvent delta P1 is given as delta P1 is equals to P1 naught minus P1 is equals to P1 naught minus P1 naught chi1. Delta P1 is equals to P1 naught 1 minus chi1, knowing that chi2 is equals to 1 by 1 minus chi1. The equation 2.23 reduces to delta P1 is equals to x2 P1 naught. In a solution containing several non-volatile solutes, the lowering of vapor pressure depends on the sum of the mole fraction of different solutes. Equation 2.24 can be written as delta P1 upon P1 naught is equal to P1 naught minus P1 upon P1 naught is equals to chi2. The expression on the left hand side of the equation, as mentioned earlier, is called relative lowering of vapor pressure and is equal to the mole fraction of the solute. The above equation can be written as P1 naught minus P1 upon P1 naught is equals to N2 upon N1 plus N2. Here, N1 and N2 are the number of moles of the solute and the solvent. For dilute solutions, N2 is very less than N1. Hence, neglecting N2 in the denominator, we have P1 naught minus P1 upon P1 naught is equals to N2 by N1, or P1 naught minus P1 upon P1 naught is equal to W2 into M1 upon M2 into W1. Hence, here the W1 and W2 are the masses and M1 and M2 are the molar masses of the solvent and the solute respectively. From this equation, knowing all the other quantities, the molar mass of solute M can be calculated. Elevation of the boiling point. We have learnt in Unit 5, Class 11 that the vapor pressure of the liquid increases with increase of temperature. If it boils at the temperature at which its vapor pressure is equal to the atmospheric pressure, for example, water boils at 373.15 Kelvin or 100 degrees Celsius because this temperature, the vapor pressure of water is 1.013 bar, that is 1 atm. We have also learnt in the last section that vapor pressure of the solvent decreases in the presence of non-volatile solute. Figure 2.7 depicts the variation of vapor pressure of the pure solvent and solution as the function of temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.103 bar at 373.15 Kelvin. In order to make this solution boil, its vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling temperature of the pure solvent, that is water. Thus, the boiling point of the solution is always higher than that of the boiling point of the pure solvent in which the solution is prepared, as shown in figure 2.7. Similar to the lowering of vapor pressure, the elevation of boiling point also depends on the number of solute molecules rather than their nature. A solution of 1 mole of sucrose is 1000 gram of water boils at 373.52 Kelvin at 1 atmospheric pressure. Let Tb naught be the boiling point of the pure solvent and Tb be the boiling point of the solution. The increase in the boiling point, delta Tb is equals to Tb minus Tb naught, is known as elevation of boiling point. Experiments have shown that for dilute solutions, the elevation of boiling point is directly proportional to the molar concentration of the solute in the solution. Thus, delta Tb is directly proportional to m, or delta Tb is equals to kbm. Here, m is molality, that is, the number of moles of solute dissolved in 1 kg of solvent, and the constant of proportionality, kb, is called boiling point elevation constant or molar elevation constant or ebullioscopic constant. The unit of kb is Kelvin kilojoule per mole. The values for kb for some common solvents are given in table 2.3. If W2 gram of solute of molar mass M2 is dissolved in W1 gram of solvent, then the molality M of the solution is given by M equals W2 upon M2 divided by W1 upon 1000, which is equal to 1000 into W2 upon M2 into W1. Substituting the values of molality in the equation 2.3, we get delta Tb is equals to Kb into 1000 into W2 upon M2 into W1. M2 is equals to 1000 into W2 into Kb upon delta Tb into W1. Thus, in order to determine M2, molar mass of the solute, known mass of solute in a known mass of solvent is taken, and delta Tb is determined experimentally for a known solvent whose Kb value is known. Depression of freezing point. The lowering of vapor pressure of solvent causes a lowering of freezing point compared to that of the pure solvent. We knew that at the freezing point of a substance, the solid phase is in dynamic equilibrium with the liquid phase. Thus, the freezing point of a substance may be defined as the temperature at which the vapor pressure of the substance in its liquid phase is equals to the vapor pressure in the solid phase. A solution will freeze when its vapor pressure equals to the vapor pressure of the pure solid solvent, as is clear from figure 2.8. According to Raoult's law, when a non-volatile solid is added to the solvent, its vapor pressure decreases, and now it would become equal to that of the solid solvent at lower temperature. Thus, the freezing point of the solvent decreases. Let Tf naught be the freezing point of the pure solvent and Tf be its freezing point when non-volatile solute is dissolved in it. The decrease in freezing point delta Tf is equals to Tf naught minus Tf is known as depression in the freezing point. Similar to elevation of boiling point, depression of freezing point for dilute solution is directly proportional to molality or m of the solution. Thus, delta Tf is directly proportional to m, or delta Tf is equals Kfm. The proportionality constant Kf, which depends on the nature of the solvent, is known as freezing point depression constant or molar depression constant or cryoscopic constant. The unit of Kf is Kelvin kilogram per mole. Values of Kf for some common solvents are listed in table 2.3. If W2 gram of solute having molar mass M2 present in W1 gram of solvent produces the depression in freezing point delta Tf of the solvent, then the molality of the solute is given by M is equals to W2 by M2 divided by W1 by 1000. Substituting this value of molality in equation 2.34, delta Tf is equals Kf into W2 divided by M2 whole divided by W1 divided by 1000. That is, delta Tf is equals Kf into W2 into 1000 divided by M2 into W1. So M2 equals Kf into W2 into 1000 divided by delta Tf into W1. Thus, for determining the molar mass of the solute, we should know the quantities W1, W2, delta Tf along with the molar freezing point depression constant. The values of Kf and Kb, which depend upon the nature of solvent, can be ascertained from the following relations. Kf is equals to R into M1 into Tf square upon 1000 into delta fusion enthalpy. Kb is equals to R into M1 into Tb square upon 1000 into delta vaporization enthalpy. Here, the symbols R and M1 stand for the gas constant and molar mass of the solvent, respectively, and Tf and Tb denote the freezing point and the boiling point of pure solvent, respectively in Kelvin. Further, delta fusion enthalpy and delta vaporization enthalpy represents the enthalpies for fusion and vaporization of the solvent, respectively. Osmosis and osmotic pressure. There are many phenomena which we observe in nature or at home. For example, raw mangoes shrivel when pickled in brine, that is salt water. Wilted flowers revive when placed in fresh water. Blood cells collapse when suspended in saline water, etc. If we look into these processes, we find one thing common in all, that is, all these substances are bound by membranes. These membranes can be animal or vegetable origin, and these occur naturally, such as pig's bladder or parchment, or can be synthetic, such as cellophane. These membranes appear to be continuous sheets or films, yet they contain a network of submicroscopic holes or pores. Small solvent molecules like water can pass through these holes, but the passage of bigger molecules like solute is hindered. Membranes having this kind of properties are known as semi-permeable membrane. Assume that only solvent molecules can pass through these semi-permeable membranes. If these membrane is placed between the solvent and solution as shown in figure 2.9, the solvent molecules will flow through the membrane from pure solvent to the solution. This process of flow of solvent is called osmosis. The flow will continue till the equilibrium is attained. The flow of the solvent from its side to solution side across a semi-permeable membrane can be stopped if some extra pressure is applied on the solution. This pressure that stops the flow of the solvent is called osmotic pressure of the solution. The flow of solvent from dilute solution to concentrated solution across semi-permeable membrane is due to osmosis. The important point to be kept in mind is that solvent molecules always flow from lower concentration to higher concentration of solution. The osmotic pressure has been found to depend on the concentration of the solution. The osmotic pressure of a solution is the excess pressure that must be applied to a solution to prevent osmosis, that is, to stop the passage of solvent molecules through a semi-permeable membrane into the solution. This is illustrated in figure 2.10. Osmotic pressure is a colligative property as it depends on the number of solute molecules and not on their identity. For dilute solutions, it has been found experimentally that osmotic pressure is proportional to the molarity C of the solution at a given temperature. Thus, pi equals CRT. Here pi is the osmotic pressure and R is the gas constant. Pi equals to N2 by V RT. Here V is the volume of a solution in liters containing N2 moles of solute if W2 grams of solute of molar mass M2 is present in the solution, then N2 equals to W2 by M2, and we can write pi V equals W2 RT by M2 or M2 equals W2 RT by V. Thus, knowing the quantities W2, T, pi and V, we can calculate the molar mass of the solute. Measurement of osmotic pressure provides another method of determining molar masses of solutes. This method is widely used to determine molar masses of proteins, polymers, and other macromolecules. The osmotic pressure method has the advantage over the other methods as pressure measurement is around the room temperature and the molarity of the solution is used instead of molality. As compared to other colligative properties, its magnitude is large. Determination of molar masses of solutes is particularly useful for biomolecules as they have generally not stable at higher temperatures and polymers have poor solubility. Two solutions having same osmotic pressure at a given temperature are called isotonic solution. When such solutions are separated by a semi-permeable membrane, no osmosis occurs. For example, the osmotic pressure associated with the fluid inside the blood cell is equivalent to that of 0.9% mass volume sodium chloride solution called normal saline solution, and it is safe to inject intravenously. On the other hand, if we place the cells in a solution containing more than 0.9% mass by volume sodium chloride, water will flow out of the cells and they would shrink. Such a solution is called hypertonic. If the salt concentration is less than 0.9% mass by volume, the solution is said to be hypotonic. In this case, water will flow into the cells if placed in this solution and they would swell. The phenomena mentioned in the beginning of this section can be explained on the basis of osmosis. A raw mango placed in concentrated salt solution loses its water via osmosis and shrivel into pickle. Wilted flowers revive when placed in fresh water. A carrot that has become limp because of water loss into the atmosphere can be placed into water, making it firm once again. Water will move into them through osmosis when placed in water containing less than 0.9% mass by volume. Salt, blood cells collapse due to loss of water by osmosis. People taking a lot of salt or salty food experience water retention in tissue cells and intercellular spaces because of osmosis. The resulting puffiness or swelling is called edema. Water movement from soil into plant roots and subsequently into upper portion of the plant is partly due to osmosis. The preservation of meat by salting and of fruits by adding sugar protects against bacterial action. Through the processes of osmosis, a bacterium on salted meat or candied fruit loses water, shrivels, and dies. Reverse osmosis and water purification. The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. That is how the pure solvent flows out of the solution through the semi-permeable membrane. This phenomenon is called reverse osmosis and is of great practical utility. Reverse osmosis is used in desalination of seawater. A schematic setup is for the process is shown in figure 2.11. When pressure more than the osmotic pressure is applied, pure water is squeezed out from the seawater through the membrane. A variety of polymer substances are available for this process. The pressure required for reverse osmosis is quite high. A workable porous membrane is film of cellulose acetate placed over a suitable support. Cellulose acetate is permeable to water but impermeable to impurities and ions present in seawater. These days, many countries use desalination plants to meet their potable water requirements. 2.7 Abnormal molar mass. We know that ionic compounds, when dissolved in water, dissociate into cations and anions. For example, if we dissolve 1 mole of KCl in water, we expect 1 mole of each K plus and Cl minus ions to be released in the solution. If this happens, there would be 2 moles of particles in the solution. If we ignore interionic attractions, 1 mole of KCl in 1 kg of water would be expected to increase the boiling point by 1.04 Kelvin. Now, if we did not know about the degree of dissociation, we could be led to conclude that the mass of 2 mole particles is 74.5 gram and the mass of 1 mole of KCl would be 37.25 gram. This brings into the light that rule when there is dissociation of solute into ions, the experimentally determined molar mass is always lower than the true value. Molecules of ethanoic acid dimerize in benzene due to hydrogen bonding. This normally happens in solvents of low dielectric constant. In this case, the numbers of particles is reduced due to dimerization. Association of molecules is depicted as follows. It can be undoubtedly stated here that if all the molecules of ethanoic acid associated in benzene, then delta Tb or delta Tf for ethanoic acid will be half of the normal value. The molar mass calculated on the basis of this delta Tb or delta Tf will therefore be twice the expected value. Such a molar mass that is either lower or higher than the expected normal value is called abnormal molar mass. In 1880, Van't Hoff factor introduced a factor I, known as the Van't Hoff factor, to account for the extent of dissociation or association. This factor I is defined as normal molar mass upon abnormal molar mass, which is equal to observed colligative property upon calculated colligative property, which is further equal to the total number of moles of particle after dissociation upon number of moles of particle before association. Here, abnormal molar mass is experimentally determined molar mass, and calculated colligative properties are obtained by assuming that the non-volatile solute is neither associated or dissociated. In the case of association, value of I is less than unity, while for dissociation it is greater than unity. For example, the value of I for aqueous KCl solution is close to 2, while the value of ethanoic acid in benzene is nearly 0.5. Inclusion of Van 't Hoff factor modifies equations for colligative properties as follows. Relative lowering of vapor pressure of solvent is P1 naught minus P1 upon P1 naught equals I N2 by N1. Table 2.4 depicts values of the factor I for several strong electrolytes. For KCl, NaCl, MgSO4, I approach 2 as the solution becomes very dilute. As expected, the value of I gets close to 3 for K2SO4. Thank you for listening. This was the end of this chapter. Kindly do the exercises and keep learning.